Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to talk on module Multiple Potential Wells, Splitting of Energy Levels and Energy Bands under the paper Quantum Mechanics. So students, let us see what we are going to learn in this module. In this module, we come to know of a potential consisting of repeating periodic identical square wells called the Kronig-Penny potential. We learn some general consequences of the periodicity of the potential. Also, we come to know how to reduce Bloch's theorem and know about Bloch waves. We study the energy band spectrum of the Kronig-Penny potential. We come to know the significance of this potential to study the energy bands in crystalline solids. In this module, we turn our attention to consider a potential consisting of a repeating pattern, or I can say periodic, of identical square wells. This potential is called the Kronig-Penny potential with a very large number of repeating units that is used as an idealized one-dimensional model to represent the effect of regular array of atoms on electrons in crystalline media. Starting from the one-dimensional Schrodinger equation, we shall discuss some general consequences of the periodicity of the potential. Here, we shall deduce Bloch's theorem and introduce what are known as Bloch waves. Finally, the expression for the energy bands are obtained and the significance of this model in the study of energy bands of electrons in crystalline solids is discussed. We start with Kronig-Penny potential with rectangular sections. Consider a potential consisting of a repeating pattern, which is also known as periodic, of identical square wells, each of width small b and depth v0, separated by identical barriers of width a prime. Such a potential, which is also shown in figure, is called the Kronig-Penny potential with a very large number of repeating units, has been used as an idealized one-dimensional model to represent the effect of regular array of atoms on electrons in crystalline media. Now, what are Bloch waves? Let us first discuss some general consequences due to the periodicity of the potential. Since the potential is periodic, so we have V of x plus n is equal to V of x, although a real crystal is of finite length. So we consider here an ideal case that equation 1 is true for all values of x over the entire range of x-axis. Thus, if psi of x is a solution of the Schrodinger equation minus h cut square by 2m into d2 psi of x by dx square plus v of x into psi of x is equal to E times psi of x corresponding to the energy E, so also is psi of x plus n. Further, since this equation is a second order differential equation, any solution psi of x may be represented as a linear combination of two linearly independent solutions psi 1x and psi 2x, that is, psi of x is equal to C1 times psi 1x plus C2 times psi 2x. Now, psi 1 of x plus n and psi 2 of x plus n are also solutions of equation 2 and may therefore be represented as linear combinations of psi 1 of x and psi 2 of x. Thus, we can write psi 1 of x plus n is equal to a11 psi 1 of x plus a12 psi 2 of x. Similarly, psi 2 of x plus n is equal to a21 psi 1 of x plus a22 psi2 of x. Using equations 3 and 4 and the fact that psi of x plus n is also a solution, we write psi of x plus t is equal to, within the brackets, c1a11 plus c2a21 bracket close into psi1 of x plus, within the brackets, c1a12 plus c2a22 within the brackets close into psi2 of x is equal to d1 times psi1 of x plus d2 times psi2 of x. This relation between the coefficients c1, c2 and d1, d2 involves the matrix multiplication, that is, the 2 cross 1 matrix with the first row as d1 and second as d2 is equal to a product of 2 cross 2 matrix with first row elements as a11, a12 and second row element as a21, a22 into a 2 cross 1 matrix with elements c1 and c2. On diagonalizing the 2 cross 2 matrix in this equation with the determinant given as a11 minus lambda, a12, the second row a21 and a22 minus lambda is equal to 0. Thus, we solve the equation which is quadratic in lambda and has two solutions, lambda 1 and lambda 2. If c1, c2 is an eigenvector corresponding to one of the eigenvalues lambda is equal to lambda I, where I is equal to 1, 2, we have d1 is equal to lambda c1 and d2 is equal to lambda c2. Thus, for the solution psi of x, there are two having the property psi of x plus n is equal to lambda times psi of x, where lambda is a constant vector. This result is known as Floquet's theorem. Of course, it follows that psi of x plus iota n is equal to lambda raised to power iota into psi of x, where iota takes up the values 0, plus minus 1, plus minus 2 and so on. Now let psi lambda 1 of x and psi lambda 2 of x be the two solutions of the Schrodinger equation 2 corresponding to the energy E, which satisfy equation 9 and correspond respectively to the lambda 1 and lambda 2 of equation 7. Let psi lambda 1 prime and psi lambda 2 prime represent their first derivatives. If W is equal to the determinant of psi lambda 1, psi lambda 2 and the second row psi lambda 1 prime and psi lambda 2 prime denotes the Wronskian determinant of psi lambda 1 of x and psi lambda 2 of x, we get from equation 9 W of x plus n is equal to lambda 1 into lambda 2 into W of x. Note that Wronskian, that is the determinant of the two functions fx and gx, is defined as W is equal to the determinant of first row f of x, g of x, second row f prime of x and g prime of x. In the present case, applying the continuity condition, that is psi 1 prime by psi 1 is equal to psi 2 prime by psi 2, have the same logarithmic derivative at the boundary. Let us now discuss the representation of the quantities lambda 1 and lambda 2. According to Wronskian theorem, if psi 1 and psi 2 are two solutions of the Schrodinger equation corresponding to the same energy eigenvalue E, the Wronskian is independent of x and is therefore a constant. Using this property, equation 11 gives the product of lambda 1 and lambda 2 is equal to 1. Now, From equation 8, if modulus of lambda is greater than 1, it is clear from equation 10 that psi will grow above all limits when x tends to plus infinity, and psi will decrease below all limits when x tends to minus infinity. Just the opposite will be true when modulus lambda is less than 1. This shows that physically admissible solutions of the Schrodinger equation exist only if the mod of lambda is equal to 1. So, using the condition described by equation 2, we may therefore represent the two quantities lambda 1 and lambda 2 in the form lambda 1 is equal to exponential iota kn and lambda 2 is equal to exponential minus iota kn. Since exponent of iota into 2 pi n is equal to 1, clearly a complete set of wave functions can be obtained by restricting the values of k to the interval k greater than equal to minus pi by n and less than equal to pi by n. Thus, all physically admissible solutions must satisfy the relation psi of x plus nl is equal to exponent of iota into lkn into psi of x, where L takes up the values 0, plus minus 1, plus minus 2 and so on, which is also known as Bloch's condition. If we write the solution in the form psi of x is equal to exponent of iota kx into uk of x, it follows from equation 15 that uk of x plus n is equal to uk of x. This is called Bloch's theorem. We find that the Bloch wave equation, which is represented as equation 16, represents a travelling wave of wavelength 2 pi by k whose amplitude uk of x is periodic, having the same period n as that of the crystal lattice. Let us now turn over to study the energy spectrum. We shall here, for simplicity, focus our attention on the Kronig-Penny potential shown in figure. This potential, exhibiting the basic features of the interaction experienced by an electron in a crystal, can be readily solved. We shall consider two cases, one for which the energy E satisfies the relation E greater than minus V naught and less than 0, and two for E greater than 0. We take up the first case where E is greater than minus V naught and is less than 0. The Schrodinger equation is d2 psi by dx square plus alpha square psi of x is equal to 0 inside the wells, and d2 psi by dx square minus beta square psi of x is equal to 0 is between the wells, where alpha is equal to the square root of 2m by h cut square into v naught plus e, and beta is equal to the square root of minus 2me by h cut square. We solve equations 18 for a given cell, that is, for example, the one extending from b minus n to b. So, we write the solutions as psi of x is equal to a times exponent iota alpha x plus b times exponent minus iota alpha x for x greater than b minus n and less than 0. And psi of x is equal to c times exponent beta x plus g times exponent minus beta x for x greater than 0 and less than b. Now, according to Bloch's theorem, the solution of the Schrodinger equation for a periodic potential has the general form given by equation 16, where the amplitude has the same period n as that of the crystal lattice. In other words, the electron does not belong to any one atom or ion of the lattice, but has an equal probability of being present in the neighborhood of any of them. Using equation 16 and equation 18, we find in the cell in the interval b minus n to b, uk of x is equal to a times exponent within the brackets iota alpha minus k into x brackets close plus b times exponent within the brackets minus iota alpha plus k into x for x lying between b minus n and 0, whereas uk of x is equal to c times exponent beta minus iota k into x plus d times exponent of minus of beta plus iota k into x. This is for x lying between 0 and b. Since uk of x is periodic, these equations determine uk of x and hence also psi of x for all values of x. As for instance, we want to write the equation function uk of x in the region x lying between b to n, so we use the fact that uk of x is equal to uk of x minus n, and upon replacing x by x minus n in equation 21a, we have uk of x is equal to a times exponent within the brackets iota into alpha minus k into x minus n brackets close plus b times exponent within the brackets minus iota of alpha plus k into x minus n. This is for x lying between b to n. In order to be a physically acceptable solution of the Schrodinger equation, the wave function and its first derivative d psi of x by dx and hence uk of x and the derivative of uk of x with respect to x must be continuous at both edges of each potential well. From equation 21, by requiring that uk of x and the first order derivative of uk of x with respect to x to be continuous at x is equal to 0, we obtain the relations a plus b is equal to c plus g and iota into alpha minus k into a minus iota into alpha plus k into b is equal to c into beta minus iota k minus d into beta plus iota k. Similarly, the continuity conditions applied at x is equal to b to the functions give the two relations as a times exponent of minus iota into alpha minus k into c plus b times exponent of iota into c into alpha plus k is equal to c times exponent of iota into b into beta minus iota k plus g times exponent of minus iota into b into beta plus iota k. The other relation is iota into alpha minus k into a into exponent of minus iota into c into alpha minus k minus iota into b into alpha plus k into exponent of iota into c into alpha plus k is equal to beta minus iota k into c into exponent iota into b into beta minus iota k minus beta plus iota k into d into exponent of minus b into beta plus iota k, where c is equal to 1 minus b. Equations 23 represent a system of four homogeneous equations for the four unknown quantities a, b, c and d. To get a non-trivial solution for the system, the determinant of the coefficients of a, b, c and d must be 0. This results in the condition cos of alpha c into cos hyperbolic of beta b minus alpha square minus beta square divided by 2 times alpha beta into sin alpha c into sin hyperbolic beta b is equal to cos kn. This gives an implicit equation for the energy E. We now consider the second case where E is greater than 0. To consider the case for E greater than 0, we require simple modifications in the treatment discussed above. Note from equation 19 that when the energy E is positive, the quantity beta becomes imaginary. We shall therefore set beta is equal to iota k, with k is equal to square root of 2me by h cut square. The equation 24 may therefore be immediately modified for the case E greater than 0 by rewriting the equation as cos of alpha c into cos of kb minus alpha square plus k square divided by 2 alpha k into sin alpha c into sin kb is equal to cos of kn. This equation can be again seen as an implicit equation for the energy E. Now, both the equations 24 and 25 can be expressed in the form of a single equation by writing f of E is equal to cos of kn, where the function f of E represents the left-hand side of equation 24 and 25. In writing this equation, we make use of the fact that left-hand sides join smoothly at E is equal to 0, so that only one equation f of E in fact is required for the full energy range E greater than minus V0. In the next slide, we give a plot of f of E versus energy E. The plot depicts the left-hand sides of equation 24 and 25. The thick lines on the abscissa show the allowed values of E corresponding to the conduction bands. They are separated by forbidden energy gaps. An important feature which emerges from this graph is that the equation 26 cannot be satisfied for certain ranges of values of E. Since k is real, we have the condition modulus of cos kn is less than equal to 1, so that the values of E for which modulus of f of E is greater than 1 are not accessible. As a result, the allowed values of E fall into the bands satisfying the condition modulus of f of E is less than equal to 1. These are indicated by thick lines in the graph described by figure 2. These bands are known as conduction bands of the lattice. They are separated by forbidden energy gaps. It can be shown that if the periodic distance n is increased without changing V0, that is, if the separation between the wells is increased, the energy bands for energies lying between minus V0 to 0 become narrower and contract in the limit n tending to infinity into the discrete energy levels of an isolated potential well. Physically, it means that as the spacing between the atoms is increased, the motion of an electron in one of the atoms of the crystal will be less, affected by the presence of the other atoms, so that each atom will behave as if it were isolated. It may be noted that Bloch wave functions, that is described by equation 16, which are traveling waves, do not satisfy the boundary condition at both ends of the chain to ensure that electrons do not escape from the crystal. This requirement, unfortunately, is not easy to implement. For this reason, we disregard the small surface effects and we adopt the periodic boundary conditions. If we consider a model of one-dimensional lattice having the form of a closed loop containing n atoms, where n is of the order of 10 raised to power 23, or I may regard it as Avogadro's number, we can equivalently formulate the boundary conditions by requiring the wave function to be single valued, so that psi of x plus small n times capital N is equal to psi of x, And from equation 15, we see that this gives the condition exponent of iota times capital N into k into small n is equal to 1. As a result, the possible values of k are discrete and are given by k is equal to 2 pi L by small n into capital N, where L takes up the values 0, plus minus 1, plus minus 2, and so on. Consequently, we see from equation 16, 24 and 25 that the wave function as well as the corresponding energy E are unchanged if k is increased or decreased by an integral multiple of 2 pi by n. We may therefore assume that k is confined within a given interval of length 2 pi by n as the interval given by equation 14. From equation 14 and 29, let us now discuss the physical importance of the results in crystalline solids. We can infer that there are n allowed values of k. As k takes each of these possible values, the energy is equal to every one of the corresponding values in each band. Thus, every conduction band contains n allowed energy levels. This result is explained if we remember that in the limit, each band contracts into single level, which is n-fold degenerate, since the electron can be bound to any one of the n atoms. For finite n, this degeneracy can be removed and each discrete atomic level spreads into a band of n energy levels. Thus, we see that above results are of considerable physical importance in the study of crystalline solids, wherein the array of atoms produces a potential forming a regular repeating pattern. We now discuss the validity of Kronig-Penny model. The Kronig-Penny model uses the idealization of treating the potential due to each atom as a square well, but the basic results obtained using this model are independent of this idealization. Specifically, the occurrence of allowed energy bands and forbidden gaps as well as the general form of the eigenfunctions, which is called the Bloch wave functions, follow from the periodicity property of the potential. So students, let us now summarize what we have learned in this module. In this module, we come to know of a potential consisting of a repeating periodic identical square wells called the Kronig-Penny potential. We learned some general consequences of the periodicity of the potential. We learned to deduce Bloch's theorem and know about Bloch waves. The energy band spectrum of the Kronig-Penny potential is discussed. The significance of this potential to study the energy bands in crystalline solids is also explained. Thank you, students, for your kind attention.